We now begin to look at the kinematics of a very important type of motion. For those of you that are enrolled, however, in Physics AB, this begins Chapter 5. For those of you enrolled in Honors Physics AB and AP Physics C, this continues Chapter 5. The type of motion is called uniform circular motion. What I'm going to do is I'm going to arrange a specific type of pendulum. I have a mass here attached to a length of string like so, and I'm going to arrange it into a pendulum that looks like this. This type of pendulum is called a conical pendulum, and the reason for that is because geometrically the string traces out a cone. However, look at the object itself. The object itself is moving at a circle that is parallel to the ground, and it's moving at a constant speed. This type of motion is called uniform circular motion. Now, even though the object is moving at a constant speed, let me ask you this. Does the object have an acceleration? The answer to that question is yes. And the reason for that is because even though the speed is constant, the direction of the velocity vector is continuously changing. And recall that acceleration is the derivative of velocity with respect to time. So then therefore there is an acceleration for this type of motion. In order to describe the kinematics of this motion, we need to know the magnitude and direction of that acceleration. Okay, let me go ahead and re-tilt my phone such that it's pointed at the board. And then let me tilt it upwards. There we go. Okay, so as indicated in my simple demonstration of the conical pendulum, we now take a look at the kinematics of uniform circular motion. So for an object in uniform circular motion, the object moves at a constant speed in a circle. However, as I indicated in the demonstration, the direction of the velocity vector is continuously changing. Therefore, there is an acceleration. Therefore, there is an acceleration. So in order to describe the kinematics of this motion, we need to find the magnitude and direction of that acceleration. Okay, now finding the magnitude and direction of that acceleration can be done very strictly by using the methods of calculus. However, by using just a little bit of geometry and some algebra, we actually arrive at the exact same result as we would by, strictly speaking, going through all the calculus. So that's how I'm going to do so here in this film. I'm going to go ahead and find the magnitude and direction of the acceleration vector, and I'm going to do so by using some geometry and some algebra. So here's then how we go about beginning to do so. Okay, let me do some erasing here. Okay, so let's say that we have the object like so, moving in uniform circular motion. For simplicity on my diagram, let's assume that the object is moving counterclockwise. Okay, now right here we'll say is the radius of the circle r, and then let's say that at times t is equal to 0, the object is right here, like so, moving in a counterclockwise fashion. So then therefore, tangential to the circle, perpendicular to the radius, we would have the initial velocity vector. So right here we'll say, like so, right there is the initial velocity vector, and it has a magnitude v. The magnitude v is the constant speed of the uniform circular motion. So v is the constant speed of the uniform circular motion. Okay, now let's say that some time interval goes by, a time interval delta t. Will eventually take a limit as that time interval delta t shrinks to 0. However, on my diagram, let's say that the object moves, say, from where I have it indicated originally to, say, right here, like so. Or once again, this right here is the radius r. Okay, now right off the bat, here's where a little bit of geometry comes in. Strictly speaking, I would have to use a ruler and a protractor to do what I'm about to do, but I'm just going to do it here by hand. Here's what I'm going to do. I'm going to take this velocity vector here, the initial velocity vector, which has this magnitude v, and then I'm going to place it right here. So it's once again going to be tangential to the circle. It's perpendicular to the radius, but I do have to draw it with the exact same magnitude as that of the initial velocity vector. So right here is the final velocity vector v. Once again, it's tangential to the circle, as is this one here. So these are right angles. And then therefore the object moves from here to here in this time interval of delta t. Okay, a couple of other things to label here on this diagram. First of all, notice that the object, as it moves from here to here, creates or subtends an angle here on this diagram. This is referred to as delta theta. And it also moves right here along an arc length on a circle, like so. And this arc length here is referred to as delta s. Okay, recall how you measure an angle in terms of radians. In terms of radians, the angle delta theta is equal to the arc length on the circle here, delta s, and then divided by the radius r. This right here is our mathematical starting point for the derivation that I'm now beginning. Okay, now once again, here comes a little bit of geometry. Strictly speaking, I would have to use a ruler and a protractor to do what it is that I'm about to do, but of course I'm just going to do this by hand. What I'm going to do is I'm going to take the final velocity vector here, and I'm going to place it right here on my diagram like so. Now when I do this, I'm just going to draw another diagram, and here's then what I obtain when I do. Okay, so right here is the initial velocity vector v from the top board, and then right here is the final velocity vector v, also from the top board. Once again, strictly speaking, in order for me to draw this, I need a protractor and a ruler, blah, 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 because we're doing this geometrically. Now, the reason why I'm drawing this diagram is because using the tail-to-tip method of vector addition, right here on this vector triangle is the change in velocity vector delta v. Recall that initial plus change is equal to final. So if this is the initial velocity vector on the diagram above, this is the final velocity vector, this right here is the change in velocity vector, delta v. On the diagram above, that delta v vector looks like this. Okay, so right here is the final velocity vector like so, and then right here is the delta v vector. Notice the direction that it's pointing in relation to the circle. Notice that the delta v vector is pointed inwards towards the center of the circle. The reason why that's important is because acceleration is the derivative of velocity with respect to time. The direction of the delta v vector is then therefore always the same as the direction of the acceleration vector. So if the delta v vector points inwards towards the center of the circle, therefore the acceleration vector points inwards towards the center of the circle. So just by doing a little bit of geometry right off the bat, we have one of the things that I'm looking for. I'm looking for example, the magnitude and the direction, that's what we just found, the direction of the acceleration vector. So let me go ahead and write this out here on the little board. So let's note that delta v points inwards towards the center of the circle. Therefore, the acceleration vector points inwards towards the center of the circle. sure that you have this written down after I have done so here. Pause if necessary to write this down. So if delta V points inwards towards the center of the circle, therefore the acceleration vector points inwards towards the center of the circle. This acceleration is given a couple of different names. It's typically referred to as the centripetal acceleration. It's also sometimes referred to as the radial acceleration because the acceleration vector is along the radius of the circle. That is, it points inwards towards the center of the circle. So this is the centripetal. Here's how you spell that word. Sometimes referred to as radial acceleration. Typically, we refer to it as A sub c. Okay, now that we've found the direction of the acceleration vector, the last thing to do is find its magnitude. Once again, we do so by using some geometry. Okay, I'm going to go ahead and do some erasing here. Of course, make sure that you have this written down, what it is that I'm about to erase. Okay, now let's jump back up to the diagram above. This initial velocity vector v here is tangential to the circle. This right here is a right angle. This final velocity vector v is tangential to the circle. This right here is a right angle. So as the object moves from here to here and it turns through an angle delta theta, the velocity vector v also turns through the same angle from this positioning here to this positioning here. On my vector triangle on the diagram here below, this angle right here on the diagram, this right here is also the angle delta theta. Now I'm not going through a rigorous geometrical proof to show that, but suffice it to say, if the velocity vectors are tangential to the circle, they turn through the same angle delta theta as the object turns through on the circle itself. Okay, now right here is an isosceles triangle. Take a look at this. This right here is also an isosceles triangle. Now you're saying to yourself, well, wait a second, delta S is an arc length here on the circle. It's a curved path. How can we think of this as a straight line? Well, this is now where we start to take into account of making the time interval infinitesimally small. So now we can begin to take a limit as the time interval goes to 0. And when we do, this arc length here on the circle becomes more and more a straight line. So then therefore what you have right here is an isosceles triangle with angle delta theta. Right here you have an isosceles triangle with angle delta theta. Therefore the two triangles are similar to each other. This then means that they have the same ratio of sides. So on the diagram above, we noted that the angle delta theta, remember, was equal to delta S divided by R. Therefore, on this diagram below, the angle delta theta is equal to delta V divided by V. Like so. And now what we do is we set this expression for this angle equal to this expression for this angle. The reason why I'm bothering to do this is because right here is essentially what we're interested in. A description of the change in velocity, and then what we'll do in just a few moments is divided by the change in time. Change in velocity with respect to time, of course, is acceleration. So I'm starting to derive for us the magnitude of the acceleration vector. So let me go ahead and take this expression here for the angle, like so, and set it equal to that expression on the board above for the angle, like so. And now what we do is we take both sides of the expression, divide it by time, and then take a limit as time approaches 0. Let me go ahead and first of all divide by time. So here on the left, I'm going to have this. So take a look at that carefully. And then here on the right, I'm going to have this. Take a look at this carefully, and now we take a limit as the time interval approaches 0. As we do, right here then is change in velocity with respect to time. This right here is the centripetal acceleration, which we now label as A sub c. And then on the right-hand side of the expression, we have here a 1 over r. And then we've got this guy right here. What is this right here describing? Well, on the diagram above, it's describing this distance divided by time as the time interval approaches 0. That is then therefore the magnitude of the instantaneous velocity vector. It's the constant speed v of the uniform circular motion. So that's this guy right here. Let's write it right here. And now the last step here to get the centripetal acceleration by itself is just to cross multiply the v here to the other side. When we do, we end up with the following expression. The magnitude of the centripetal acceleration vector is equal to the speed squared divided by the radius. That's the magnitude of the centripetal acceleration vector. So at this point, let's just kind of summarize where we are at this point. So here's a little summary thus far. So in my demonstration of the conical pendulum, basically you have two vectors that are circulating on the diagram. So let's say that right here is the circle, like so. Okay, right here is the radius vector, and then tangential to the circle, right here is the instantaneous velocity vector v, like so. Okay, that's one vector, but the second vector is now the centripetal acceleration vector. The centripetal acceleration vector, a sub c, points inwards towards the center of the circle, like so. Right here is a right angle, and the magnitude of the centripetal acceleration is equal to the speed squared divided by the radius. So these two vectors here, my index finger for the velocity vector and my thumb for the acceleration vector, they're circulating on the diagram like so as the motion occurs. So watch what happens a quarter of a revolution later. A quarter of a revolution later, the object is here at the top of the diagram. Here's the radius in blue once again. Right here is the initial velocity vector. Right there is the final velocity vector, tangential to the circle and with the same magnitude, like so. So there's my right angle. And then we have right here the centripetal acceleration vector, inwards towards the center of the circle. That's right here as well, still pointing inwards towards the center of the circle. That then looks like this. A little bit later on, after we complete the kinematics here of uniform circular motion, then we'll go through all the F equals ma, all of the dynamics that causes all of this. That is what causes the centripetal acceleration. We'll get to that a little bit later on. But for now, we're just describing this motion. The magnitude of the centripetal acceleration vector is the speed squared divided by the radius, and its direction is inwards towards the center of the circle. This right here is the most important aspect of the kinematics of uniform circular motion. The remaining kinematics for our purposes is actually just a series of definitions at this point. So let me do some erasing here on the board like so. I am, however, going to keep the diagram above. Like so. Okay, and now we've got a couple of definitions. You're actually already familiar with these definitions. The first of these definitions is what's called a period, which in this context is referred to as capital T. The period, capital T, is the time necessary for one revolution to occur. Okay, that's very much related to another definition that you have also heard, and this is what is called frequency. Frequency is abbreviated as small f. Frequency is the number of revolutions that occurs per second. Okay, now frequency is a new quantity for us, so let's go ahead and check the units. Anything that is a number per second is given its own name. It's referred to as hertz. It's named after somebody, and it's abbreviated as Hz. Like so. There's a very simple relationship between frequency and period, and here's how you can discern that relationship. Let's say the frequency is 1 hertz, and it would be 1 hertz, by the way, not 1 hertz, because hertz is somebody's name. So let's say that the frequency is 1 hertz. What that means is that 1 revolution is made per second. So then therefore, think about it, what is then therefore the period? That is the time necessary for 1 revolution to occur. It's just 1 second. Let's say that the frequency is 2 hertz, so 2 revolutions are made per second. Therefore, what's the period? That is the time necessary for 1 revolution to occur. It's a half a second. Notice that frequency and period are inverses of each other. Like so. Okay, now we can begin to relate frequency and period to the other definitions involving speed and acceleration from earlier in this derivation in the following way. It has to do specifically with the speed v. Now, if you go all the way back to the early portion of our unit in kinematics in chapter 2, remember that speed is defined as distance divided by time. However, when talking about uniform circular motion, a very useful distance to use is the circumference of the circle, like so. And then therefore, in the denominator of the expression would be the time necessary for one revolution to occur, one complete circumference, and that's of course the period, capital T. So then therefore we begin to relate the speed to these new quantities involving the period and the frequency by using this expression here. Once again, this is just distance over time, nothing more than that. Sometimes you'll see this expression written not in terms of the period, but instead written in terms of the frequency. Sometimes you'll see it written as the circumference multiplied by the frequency, like so. Okay, and then lastly, there's one more definition. And this is what is referred to as angular speed. Angular speed is referred to as omega. This is not a letter W, this is a lowercase Greek letter omega. Omega, by definition, is equal to change in angle divided by change in time. So then therefore, it's how much angle the object rotates through per second. It's usually measured in terms of radians per second. Okay, now angular speed is related to the other quantities that I have here on the board in the following manner. Let's jump back up to the top board for just a moment. Remember that I started this process 10-15 minutes ago by using this expression here for the angle on this diagram. But notice that if I take this expression and divide it by time on both sides of the equation, then I'm going to start to come up with a description of the angular speed. So let's go ahead and take this guy from earlier and now divide by time on both sides. Like so. And then we'll once again think of this in terms of taking the limit as the time interval approaches 0. But when we do, right here is the angular speed omega. Like so. And then on the right-hand side of the expression, remember from earlier that this right here is just distance divided by time, which is the speed v of the uniform circular motion. Sometimes, by the way, in this context, the speed v is referred to as the linear speed, just to distinguish it from the angular speed that we're describing here. So then therefore, the angular speed omega and the linear speed v are related to each other by means of this expression. More times than not, by the way, you'll see this expression written with the r moved up to the other side, such that v is equal to r omega. So now at this point, I can summarize the kinematics of uniform circular motion. Basically, what you end up with is just a bunch of little expressions. So let me do some erasing here and just briefly list those expressions. Okay, so once again, here's a nice summary. Okay, we first of all have the centripetal acceleration, which is the speed squared divided by the radius. We have the definitions of the frequency and period and their inverses of each other, and then speed equals circumference divided by period, or equivalently circumference multiplied by frequency. And now we've got this new quantity, the angular speed omega, which is related to the linear speed v through this last expression. V equals r omega, like so. Sometimes you'll see the expressions, by the way, combined a couple of different ways. Take a look at this description for the speed, and then right here, this description of the speed. In this description of the speed, what is the omega? Well, if you look carefully, you'll notice that it's 2 pi divided by the period. So sometimes you'll see this expression here also for uniform circular motion. This makes sense because how much angle does the object rotate through in one full period? It rotates through the entire circle, that's 2 pi radians. You'll also sometimes see omega, by the way, written as 2 pi multiplied by the frequency f. Like so. There's a couple of other ways in which the expressions are combined, but doing so in this manner, these are the basics right here. So once again, for the kinematics of uniform circular motion, you end up with a bunch of little expressions. Okay, using these expressions in basic examples is easy to do. That's what we'll do next.